Okay. So, in the last two classes, last three classes, we have discussed about the mathematics of transduction. Okay. Transduction we have discussed. Now, what is required? Let us start with the microphone. Now, suppose as a, if you say that you have done that audio system engineering course and somebody told you, can you show me or can you say something about the what kind of microphone I should select for this purpose of application? Okay. That means, or how can I design a microphone of this kind? These are two questions can be asked by the society. One is that, yes, I want to record this kind of things, what type of microphone I should use, or I can say I require this kind of application. So, which microphone will be suitable or how to design that microphone. Okay. Now, suppose you go for a market, go to the market and find out which kinds of microphone is suitable for your application. How do you decide it? So, as you know that when you go for the shopping, you have asked for that, suppose you want to buy a TV or buy a washing machine. As an engineer, when you go for the shop, what kind of questions you ask or what document you want to see from before buying that washing machine? That is called technical specification. Means there is certain parameter written on the if you see any data sheet or any technical specification of any systems, there are certain parameters are written on that data sheets. You have to know which parameter is meaning what, then you can suggest which machine is suitable for your purpose. Similarly, when I buy a microphone, what kind of specification I should see? Let us first discuss that part. First one is called frequency response. So, which is that means that is the requirement. Specification means that somebody said me that I want to record this kind of performance, which kind of microphone or I should buy. So, you are seeing the specification of the microphone. On the vice versa, it is a requirement of the user. So, I require this kind of microphone. So, you can convert that requirement to the microphone specification. So, that is nothing but a requirement of the professional microphone. What things you should look at? One is that frequency response. One of the point is called frequency response. So, what is frequency response? If you see in anything, if you see that when you buying a audio systems or when you buying a microphone or when you buying a loudspeakers, always you will ask what should we, or if you see that you want to buy a IC also, that if you are electronics engineer, you know, so every IC there is a frequency response curve in the data sheet. Okay. So, what do you understand by the frequency response of the microphone? Suppose, what should be the ideal frequency response? Nothing is given. What is the ideal? That human audio range is 20 hertz to 20 kilohertz. So, if I say what should be the good microphone, I will always say if all the frequency up to 20 hertz to 20 kilohertz has the same response. Frequency response curve should be like this. What is the frequency response curve means? This is called the sensitivity, this axis, and this axis called the frequency. So, sensitivity of the microphone should be equal in all frequency. That means, I cannot say that if sensitivity I come later on. So, I cannot say suppose I producing the same pressure P for all frequency of 20 hertz to 20 kilohertz, the output, electrical output of the microphone should be remain constant. That means, if I apply a 1 kilohertz P pressure and if I get the voltage V, then if I apply a 2 kilohertz P pressure, I should get voltage V again. Then I said the frequency response of that microphone is flat. But in practical, frequency response is, I cannot get the frequency response all in flat. If you say what is the human frequency response of the human ear, human ear are not all frequency are all sensitive. So, all frequency are not equal sensitive. If you remember, we have said that loudness curve, that during the frequency versus the loudness curve, that if this is the frequency, this is the audio range. This means if it is set the 0 dB, so same loudness of different frequency are not perceived the equal loud. Or you can say the if I say 10 dB of 20 hertz 10 dB and 20 hertz 10 dB and 1 kilohertz 10 dB, both will be not perceived equally loud, because of the frequency response of the outer ear and inner ear is like this. Then human also does human being also perceive to perceive the low frequency, I require a larger amplitude, pressure amplitude than the high frequency. On also very high frequency, again the frequency response, the sensitivity of the ear goes up. So, depending on the requirement, see the ultimately the microphone actually what I required, that I will catch the signal by microphone, then again convert to the loudspeaker, and that should be listened by a human being only. So, I can say, okay, since the human frequency response is not flat, I may not require a very flat frequency response of the microphone. So, I may require a frequency response of microphone if like this. If you see, this is the Shure SM57 micro from the data sheet. The frequency response at 20 hertz does not required. He said human voice 20 hertz is audible, but if it is purpose for the voice recording or music recording, I said below 20 hertz I may not required. So, if you say at here response is same and it is down. So, after roughly 200 hertz I get flat response up to maybe it is up to maybe 1.5 kilohertz, or no not 1.5 kilohertz, this is 1 kilohertz, then this is 10 kilohertz. So, up to 10 kilohertz roughly it is flat and then it is going down, and here slightly upper sensitivity is there. So, I have no problem. So, I can say this microphone may have a frequency response of let us 300 hertz to or 200 or let us 100 hertz to 10 kilohertz. So, I said microphone has a frequency response 100 hertz to 10 kilohertz. Actually, this is measured in a 3 dB down. If I have a frequency response like this, then I can say frequency response from here it is 3 dB down, from if it is 0 dB, then 3 dB minus 3 dB, that side minus 3 dB. So, this F1 to F2 is the frequency response of that microphone. Okay. So, if I say that I want to record a music, it may not be say that music is required let us 200 hertz to at least 18 kilohertz. But if I say I want a microphone to capture the audio signal and transmit in a telephone channel. So, the telephone channel bandwidth let us 8 kilohertz sampling frequency, so 4 kilohertz. So, above 4 kilohertz I do not require that signal. So, I can say okay, I can buy a microphone, a telephone channel is 300 hertz to 3.3 kilohertz. So, I can say 30 hertz to 3.3 kilohertz is okay. Then I can say I want a microphone whose response is 300 hertz to 3 kilohertz is flat, and rest of the I do not bother. Okay. So, this is the frequency response, meaning of that frequency response. So, now there is a problem. What is the problem? Now, if I want to increase the frequency response, the cost of the microphone will be very high. That means, if I have a wide range of frequency response, means suppose I want a microphone who has a 100 hertz to 20 kilohertz flat frequency response, cost may be very high, because the construction of the microphone, if you see in the design time, the construction of the microphone is very costly. Okay. So, this is the meaning of the frequency response. Then next parameter will come. So, this is I have covered transient response. So, I suppose I design a microphone, sudden change in pressure, sudden large pressure change should not be change in output voltage of the microphone also suddenly. So, I want the microphone is working, but if I apply a pressure impulse like this graph, my transient response should be as much as flat is possible. So, transient response should see the transient response for a dynamic microphone, transient response for a ribbon microphone, transient response for a condenser microphone. So, what is dynamic microphone? Electrodynamic microphone, ribbon microphone and condenser microphone. We will study that all kinds of microphones, what is the kinds of microphone. So, I require a transient response should be very low, very not sharp high. If it is sharp high, then it creates an disturbance or noise in the recorded signal. Next one is sensitivity. So, I said sensitivity I have already said in during that frequency response. So, what is sensitivity? The word sensitivity is that if you say that this person is very sensitive to this thing, what is the meaning? Meaning is that the amount of stimuli you applied and the reaction. So, that there is a measurement between the amount of stimuli I applied and the reaction. So, in case of microphone, the sensitivity is that sensitivity defined as a that if I apply a pressure, what should be the electrical output. So, sensitivity of a microphone is 0 dB if I apply a 1 Pascal pressure on the microphone, if it is produced 1 volt at the electrical circuit. Okay. So, if I say the sensitivity is defined voltage per Pascal, voltage per Pascal. Now, if it is written like this 20 millivolt per Pascal, what is meaning? That if I apply a 1 Pascal pressure on the microphone, it will give me 20 millivolt. This is sensitivity. Now, is the sensitivity frequency independent? If I apply a 1 Pascal pressure of 1 kilohertz and 1 Pascal pressure of 5 kilohertz, are they produce both 20 millivolt or they produce different? That depends on the frequency response of the microphone. If the frequency response of the microphone between 1 kilohertz to 5 kilohertz, then it should produce 20 millivolt. So, on the vice versa, the sensitivity of the microphone depends on frequency. How it is depends on frequency, let us see. So, I said let sensitivity of the microphone is defined is M0. So, M0 is nothing but a voltage per pressure, voltage per pressure. So, what is pressure? Voltage per force per unit area. Pressure is nothing but a force per unit area. So, force by A is the force. So, it is nothing but a V into A by force, where V is the open circuit output voltage. The condition, yes, sensitivity is measured at the condition when the microphone is in open circuit. That means, microphone is not connected to other device, the load is not applied to the microphone. Okay. So, open circuit voltage sensitivity of the microphone if M0, then the open circuit voltage divided by the pressure amplitude P, and pressure is nothing but a force per area. So, V into A by F. Now, what is V? V is, as you studied, that JDB blocked electrical impedance into I plus phi m u, phi m u. Okay. Now, if at I equal to 0, V is nothing but a phi m by phi m into u, V is nothing but a phi m into u. So, I can write phi m into u into a open circuit voltage. That means, there is no current flow. So, I equal to 0. So, I equal to 0 means V equal to phi m into u. So, phi m into u A divided by f. So, it is nothing but a phi m into A u by f. What is u by f? Z m o, open circuit mechanical impedance, is nothing but a force by velocity. So, I can write this is nothing but a phi m A divided by Z m o. So, what is Z m o? Z m o depends on the construction of the, so Z m o may be either if it is a moving coil or if it is a electrodynamic transducer. So, Z m o is nothing but a R m plus j omega m minus S by omega. So, our Z m o is depends on frequency. So, I can say sensitivity m 0 is also depends on frequency. Okay. Now, how do you make a flat frequency response? I want, so what is my motivation? I want that m 0 should be frequency independent for a particular range of frequency. Okay. So, I have to make Z m o frequency independent for a particular range of frequency, then I can say the microphone sensitivity is that particular range of frequency, sensitivity is frequency independent. That means for within that range, for every frequency the sensitivity will be same. So, that is the frequency response of the microphone. So, how to make is m is frequency independent, it depends on the how you design. If I design the microphone such a way that it is m, that Z m o is frequency independent, then I can say yes, microphone is in for this particular frequency range, microphone sensitivity is frequency independent. So, characteristics frequency curve or frequency characteristic of the microphone is flat during that range. Okay. Another one is that directivity. You know that directivity, the directivity pattern, we said the directivity pattern. What is directivity of a microphone? Now, if you see in the collar mic, if I speak from this direction, it is catch. If I put the mic in reverse direction, it might not be catch. So, that means microphone has a specific direction to catch the sound pressure. Okay. So, directivity pattern should vary a little as possible with frequency. This is the one requirement. I have said that okay, directivity patterns directional response should vary as little, that is the requirement of the microphone, and directivity pattern also not frequency dependent that much. Okay. So, if it is frequency independent, then how do you make the directivity? So, a microphone sensitive to sound relative to the direction or angle from which the sound is arrived. So, you can read the slides, I will give you the slides, you can read. So, do not read that, I am not reading the slides. So, what is there? So, suppose I have a microphone like this, and if microphone only catch from this direction of the sound, then has a directivity. The directivity pattern of the microphone always draw in polar coordinate. That means, suppose I have a microphone here, if the microphone direction is this side, then I will write this kind of pattern. This is called the directivity of the microphone. Okay. So, a microphone based on the directivity can be three types. One is called omnidirectional microphone, unidirectional microphone, and bidirectional microphone. What is omnidirectional microphone? If you see this directivity pattern for omnidirectional microphone, sound coming from any direction, microphone will sense or microphone response will be the same. If the sound coming from the top, bottom, side, any angle of that microphone, the directivity, if the omnidirectional mic, sensitivity will be remain same. Okay. Then it is called omnidirectional microphone. What is bidirectional unidirectional microphone? Uni means only single side. That suppose I have a microphone that only catch this side, then I call say it is a unidirectional microphone. This area, if the sound is coming from this area only, the microphone will be sensitive. On the other side, microphone is not sensitive. So, if we see that unidirectional microphone plot is like that, blue line indicate the directivity of that microphone. This is the microphone position. So, if it is this, you see only this direction microphone is catch. If you speak from this direction, only microphone will catch. If you speak from this side, microphone will not catch. So, when you put a microphone like collar mic, why I put this one is top side? Because I said this is not a omnidirectional microphone, it is a unidirectional microphone. Directivity pattern is in upside. So, if I put it up, if the sound pressure is coming from upside, it catch very good, or its sensitivity is good. So, that is why I put the microphone in this way. If you stage, you see that microphone, the loudspeaker, the microphone, the speaker is speaking from the front side of the microphone. That means the directivity pattern of the microphone is front. If you say in the stage, earlier that there is a catcher. So, catcher directivity pattern is this side only, not back side. Top of the stage nobody is there. So, I cannot, I do not require the sound should be catch from this side. I only require the sound should catch from this side, sound should catch. Okay. So, this is the directivity pattern. So, there is a bidirectional microphone which can take the sound from the both the direction. So, it is like nothing but a figure of 8. So, if it is both are same, then it is a figure of 8. If it is depending on the directivity pattern on both sides, the microphone are two types, supercardiate and hypercardiate. Only the debate, I am not saying that, just you can read the slides on that things. Okay. Then what is else is required? Self generated electrical noise, you should check. So, you check the frequency response, you check the sensitivity, you check the transient response, you check the directivity pattern of the microphone. So, suppose I want to use the microphone for lecturing, then I may be unidirectional mic is very enough, this unidirectional mic is enough. But suppose I want the microphone, I should put the microphone here and the both side of that speaker will be seated, then I may require a bidirectional microphone. Or suppose I put a microphone here in any side, any front, any point of any direction a speaker can say I want the catching. So, I put a unidirectional microphone. So, depending on the type use of the microphone, you should choose the directivity pattern. Next one is self generated noise, electrical noise. If the self generated electrical noise is high of the microphone, then it will be amplified, the noise also will be amplified and the output of the loudspeaker will be very bad. Then in environmental influence, if I construct a microphone, if it is very very fine in during this AC environment, if it is go to outside, it is not working. That means it should not be temperature, humidity, magnetic or electric field change. So, it should not be, suppose this is a dynamic mic and I have a magnetic field is here, the magnetic field strength is B in here. If I change its strength, if it is change in outside, if I change the position of the microphone, magnetic strength is changed, that will not work. So, I want the microphone should work with a humid or with different temperature, electric field and magnetic. Suppose I put the microphone in here and there is a high voltage line is going on. So, microphone should not be interfered by the high voltage line. So, that kind of microphone I want. Should be mechanically robust, reliable, lightweight, not too expensive. This is the customer, this is the point to discuss. So, if I want a very good sensitive microphone, very good frequency response microphone with a very high sensitivity, I cannot get a low cost, the cost will be high. Similarly, I want the microphone should be very robust, it should not be handled with care, and if I just connect little bit of tight, then it will tear up. That kind of microphone we should not want. We want the robust microphone. Then we want lightweight, it should be very heavyweight. If it is heavyweight, if the collar mic is heavyweight, I cannot put it in here. So, I require a lightweight microphone. So, depending on the application and cost and the requirement, you should choose your microphone based on those parameters. Okay. Now, I go for the component of the microphone. If I want to design a microphone, what are the basic components? First one is the diaphragm. I can show you in the next lecture the diaphragm of a microphone. I can show you in the next lecture the diaphragm. A thin light membrane which moves in response to sound pressure variation. So, diaphragm, as we discussed in transduction during the anti-reciprocal and reciprocal transducer, the diaphragm is a thin membrane which can move due to the sound pressure. So, if microphone diaphragm, it is exposed to the sound pressure and it should move, and this mechanical movement will create the electrical variation. Okay. Transducer usually coupled to the diaphragm. What is the work? You have already studied the transducer principle. Based on the principle of the transducer, it should convert that mechanical energy to electrical energy. Convert the mechanical energy to electrical energy. Or you can say, if I apply a low sound pressure, it should create a voltage or current depending on the requirement. Then casing, diaphragm, transducer, and it should be casing in a very rigid casing, so that it should be environment rugged and it should be environment friendly. So, enclosure, part enclosure, diaphragm and transducer, nature of the casing determine the directional response of the microphone. Casing has another important parameters, that depending on the casing, the direction of the microphone will be determined. Means, suppose if my diaphragm is here and we put that microphone is a this kind of metal casing. So, and here is the opening, then the sensitivity of the microphone will be this side. Okay. Sensitivity microphone will be this side. So, I can say the directivity pattern of the microphone will be like this. If I say this microphone, if you see it, that top side all are enclosed, only top side is perforated. That means, voice pressure is coming in the top side and it is directivity pattern is in the up. Okay. Then basic microphone type, those are the basic component. Depending on the construction of the microphone, there are different types of microphone: carbon microphone, piezoelectric microphone, dynamic microphone, condenser microphone, electret microphone, ribbon microphone. Carbon microphone, piezoelectric microphone, dynamic, depending on the construct, how do you make the microphone, those are the different type of microphone. There is a boundary layer microphone, there was the application type, boundary layer microphone, tabletop microphone, boom microphone, but construction wise, carbon microphone, piezoelectric microphone, dynamic microphone, condenser microphone, electret and ribbon. Those are the basic types of the microphone depending on the construction of the microphone. Okay. Carbon microphone, as already, have you seen any? If you see today there is nothing, no carbon microphone is used, but if you see the earlier telephone, that cradle telephone, black one, there is a carbon microphone. If you see that there is a cradle type microphone and is a huge cradle in this side and then this side also a cradle. Okay. So, that microphone was carbon microphone. So, the basic principle of the carbon microphone, you know that. So, this is the construct, this is written, you can see that, you can read that slides. So, there is a diaphragm connected with a metal and there is a capsule, brass capsule, and within the capsule there is a carbon granules. So, if the diaphragm is connected to the this metal with a pin, and then if the diaphragm is vibrate in this side, pressed in this side, this also pressed in this side, and carbon granules will be displaced and resistance of this between these two electrode will be changed. Here is a electric connector, so there is a connector here and here is a connector. So, if the resistance is changed, the change of current will be happen, and I put a transformer here. So, the change of current induce a voltage in here. So, I can say that this is the signal output. So, depending on the motion of the diaphragm, the resistance will be changed. So, change of resistance create the output. If you want to see the simple mathematics on here, I say that, so actually what is happening here, R0 is the static resistance of the granules, then R is the dynamic resistance, means if it is changed then it will be R. So diaphragm is moved in x distance. So the R will be R0 plus H into x. What is H? Resistivity of the carbon granules. So if the x distance change, H multiply by x, or resistance constant or resistivity, Q per ohms per meter, ohm per meter. Okay. So H is nothing but a ohm per resistance constant or ohm per meter. Now if I say how do you derive x? Diaphragm has a motion u. The diaphragm is exposed to a pressure and has a motion, but velocity is u. Then u is nothing but a j omega x d dx. U is nothing but a dx of dt. So d dt can be written as a j omega x. So u is nothing but a j omega x. Okay. So what is j omega? What is u? What is u? U is nothing but a force divided by mechanical resistance. U is force divided by mechanical resistance, force by ZMO. So if the diaphragm is exposed to the force F, then force by ZMO is the u. What is force? Force is nothing but a pressure multiplied by the area of the diaphragm. Pressure is nothing but a force per unit area. So it is pressure multiplied by the area of the diaphragm. So I can write that u is nothing but a let's F divided by what is ZMO, Rm plus j omega m plus 1 by, or you can say S by omega. Okay. ZMO. Now if it is u, then if omega is less than omega 0, what is the meaning? The operating frequency of the microphone is very low compared to its resonant frequency omega 0. Then and Rm, mechanical resistance, is very low compared to 1 by omega. Then and another omega m is much less than S by omega. This is the three condition. Microphone is operated below the resonance, well below the resonance frequency. Resistivity or mechanical resistance of the microphone well below the 1 by omega, and omega m is much less than S by omega. Then I can say u is nothing but a F by Rm plus j omega m plus omega m, sorry, j omega m by S by omega. S by omega. So I can say in that case, if it is that, then I can say okay, this plus or minus, it is nothing but a F j omega by S, if all these three limitations are applied. Okay. So now j omega x is equal to nothing but a F j omega by S. So x is nothing but a F by S. So it is nothing but a pressure Pa by S. So R now come R0 plus H into Pa by S. So I is nothing but a current is nothing but a voltage by resistance V0 by R. So if I say initially I have applied V0 in here, 6 volt battery. So it require a battery. I applied a V0 in here. Now the resistance is changed, total resistance is changed. So I can say I will be changed from V0 by R0 plus H into Pa by S. Okay. Then I can write, then it will become, then I can say I is change. Okay. So, now current is change. So, I can, this current will be taken by the transformer and we can get the equivalent current of the pressure. Okay. So, this is the resistance microphone, which is almost obsolete from the markets. You cannot get the resistance microphone today. Okay. Next one is piezoelectric microphone, where diaphragm is mechanically coupled to a piezoelectric crystals. You know that if I deform a piezo crystal, then it change its polarization and it produce a charge difference, and which can induce a current, or which can flow a current or voltage, or we can get equivalent voltage. So, that is the basic principle. So, if you see the construction, there is a diaphragm connected to a piezo crystal by a pin head. Diaphragm mechanically coupled to a piezoelectric material. Piezo, you know the piezo material, what are the piezoelectric material? Then what is happened, that if I, so if you see it here, forget about the, read the slides. If I generate a pressure in here, if I apply a pressure on the diaphragm, the pin will put a pressure on the piezo and it change its direction, and then there will be a equivalent charge difference, create a current. If it is diaphragm is moved this side, then also it change its direction and it produce a current. So, change of direction of the piezoelectric crystal produce a current. Okay. So, that is the mechanism for piezoelectric microphone. Now, what is the property? The microphone cable should be very short, less than 1 meter, to reduce the effect of induction from adjacent electrical circuit. So, main drawback of the piezoelectric mic is a very cost effective solution, a very cheap mic, because construction of the piezoelectric mic nothing but a diaphragm connected to the piezoelectric crystal by a short pin. Okay. Now, it is very cheap, but the problem is that the amount of the charge which is given by the two wire is very much sensitive to the induction from the adjacent circuits. So, if I take a long cable and there is a lights and fan and everything, so induction charge also the current will be interfered by that induction. So, the sensitivity is very less, or the sensitivity is minus 30 dB per Pascals, 30 dB or 1 volt or 30 dB per 30 dB. So, minus 30 dB is the sensitivity. So, I can say the length of the cable is less. That is why if you see your headphone may be a piezoelectric mic, but I cannot connect a piezoelectric mic in a dais, because the long cable is required. So, piezoelectric mic a cheaper solution of microphone, and it can be used for a short distance microphone, because it is very rugged. It only have a diaphragm, pin and piezoelectric crystal. Load impedance need to be very high. If a piezoelectric mic is connected, then it requires a very high low impedance, and sensitivity level is minus 30 dB, no polarization voltage is required, generally rugged. So, sensitivity and frequency response stable with the time, humidity and temperature range. So, no problem. Sensitivity is if I put the microphone 1 year, sensitivity does not change that much. Okay. So, sensitivity, the microphone is very rugged, but only drawback is the cable should be very short, and the frequency response is reasonably good, but not very good. Okay. Then we go for another microphone is called moving coil microphone. Construction of the moving coil microphone is already I have discussed, the magnet, coil, dome, diaphragm, then or diaphragm, and then it connected the housing in a casing, or you can say this is a suspension or mechanical resistance come from this suspension, and then this coil may be either aluminum or copper. Okay. Now, I am not going to that things. So, changing current in the coil follow the pressure variation in the diaphragm. The EMF generated is in the order of 0.5 to 1 millivolt for speech at a distance from 0.5 meters. Generally, quite robust and unaffected by humidity, because nothing to change with the humidity in here. Very slight change in diaphragm weight maybe increases, but not that much of, not affected by the humidity. Expensive as assembly need considerable skill. Diaphragm and coil must be lightweight and low output impedance, good with long cable. So, all the stage microphone, if you see, I have required a long cable, I required a dynamic mic, and it is also very rugged. Then there is another kind of microphone, ribbon microphone. So, there is a ribbon in a magnetic field. If I apply a pressure, ribbon will move, and that induced voltage will be create the signal. Okay. So, ribbon microphone is small, but a stipulated voltage transformer is often used to increase the output voltage, similar to moving coil microphone, and impedance is below 30 ohm. Stable for pressure gradient microphone. I will come what is pressure gradient microphone. So, ribbon mic is used for pressure gradient microphone. Then electrostatic microphone, as we discussed, capacitive microphone. So, moving coil microphone and capacitive. Ribbon microphone is also a electrodynamic microphone, but instead of coil I put a ribbon there. So, ribbon is nothing but a some wire pasted on a very thin insulated material. So, it is nothing but a moving coil microphone, but it is construction wise it is called ribbon microphone. Electrostatic microphone, you can read the, I will share the slides. So, to remove the there is a time constant. So, I am not reading the slides, and I am not, I just discuss what is electrostatic microphone earlier. So, it is same in the here also written, and the construction is given. So, you know that there is a MD-CD-CB which is come from the microphone side, and MB-CB I have already discussed what is there. So, electrostatic microphone, it work on a plate. So, there in between two plates I apply a DC fixed DC voltage initially, and then if I apply a alternative current, or if I apply a pressure, if I plate distance is changed, it produce the change of capacitance and produce the change of current, and that act as a signal, I get a signal. So, that this how this voltage will be connected is very important. So, capacitance microphones required a power supply. Without this V0, capacitance microphone will not work, and V0 connected to the capacitor with a large input resistance. So, that this when I apply a signal, when the diaphragm is vibrate, that AC signal should not flow in the battery side. Okay. So, this is the main drawback in capacitance microphone. So, if you see the piezo mic, it does not require any power supply for operation of the microphone. Dynamic mic, moving coil microphone, it does not require any power supply, DC power supply for the microphone. But for the piezo mic, for the capacitance microphone and carbon microphone, I required a DC supply, which is the main problem. So, suppose I want to, I have a computer and there is a line in, if you see there is a line in means there is only RCA jack is available by which I can connect a microphone. Now, if I connect a capacitance microphone, is it work? If the capacitance microphone does not have the battery within that microphone, then it does not work. So, if you see there is a some amplifier earlier that, or there is a some amplifier where I can use the capacitance mic, that means a DC supply will be supplied from the amplifier to the microphone by a circuit, by a very high resistance, and then that then the signal will be transferred to the amplifier. So, if you see the properties of that microphone, I have not discussed about that this part. Two method, there is a two method for putting. So, I said that in capacitive microphone I required a initial charge. So, in the order of 1000 1000 10 to the power 5 volt per cm cubic meter cm per cm. So, in that order how can I put the charge on the capacitive microphone? There are two procedures. One is I supply a battery or I put a battery on the microphone or supply the DC supply from my amplifier to the microphone. That is the one, that is the procedure 1, and it should be supplied through a high value resistance. So, that RC constant, time constant, which make Q to be effective constant. Okay. And figure, you will see the figure. And second method is putting a charge on capacitor to use electrode. So, I can use a electrode and charge the electrode, and that microphone will hold the charge, electrode should hold the charge. But it is, if it is humidity, there is a humidity, then my electrode may discharge. So, if it is discharged, then sensitivity of the microphone will goes down. So, by electrode it is not that good, but putting a DC supply on the microphone is a very good arrangement. So, how do you do that? If you see, this is the microphone and this is a DC. So, there is a high value resistance DC supply connected to the microphone with a high value resistance, and then I put a capacitance and to go to the preamplifier, or I can put a electrode material to charge it. So, like that way it is charged, you know that electrode material how it is charged. So, directivity pattern. Now, I go for the all kind of microphone I discussed, then I go for the directivity pattern or polar diagram. Directivity pattern is in polar diagram. Now, microphone, how the microphone is work? Either, suppose this is the diaphragm, either the pressure which is coming from the source or acoustic source should fall on the diaphragm, and diaphragm vibrate and produce the electrical voltage. So, it is a pressure sensitive microphone. So, that means the change of pressure create the vibration of the diaphragm and microphone work, microphone produce the voltage. So, that is called pressure microphone or pressure sensitive microphone or zero order microphone, zero order gradient microphone. Then there is another kind of microphone which is called velocity microphone or pressure gradient microphone. It work on difference of pressure both side of the diaphragm, that is the velocity microphone. So, pressure microphone, the diaphragm is exposed to the sound source only in one side. If I want to make the pressure microphone, that if this is the diaphragm, this is the diaphragm, then it should be exposed in this side only, not this side. If I expose this side, then the vibration will be not come. So, I encapsulate that, I make the enclosure in back side and put the only open in the top side. Then this microphone will be the pressure microphone. Okay. Directly proportional to the sound pressure. Directivity pattern depends on the relationship between the wavelength and diameter of the diaphragm. When the diameter, the lambda is very greater than the diameters, sound from all directions strike the diaphragm, those from back arrive by diffraction. So, you know that if the sound diffraction, if I put this is the my diaphragm, that the acoustics wave are coming out, the waves which has lambda is much greater than the diameter of the microphone, that can diffract and easily come to the and if it is not that then if it is from the all directions strike the diaphragm, those from back also arrive in diffraction. Directivity pattern is omnidirectional, because microphone diaphragm is open in only one direction, that is why the directivity pattern of the microphone is omnidirectional. When the wavelength is comparable, this is not that much important. So, as if you see, there is a microphone diaphragm exposed to a that side only. There may be a very little hole in here, because if the sound pressure increases, that to make it, if it is completely enclosure, the sound pressure inside this enclosure, if there is some pressure is developed, then the diaphragm movement will be affected. So, I put a small aperture in here, and this aperture also cancel this wavelength is comparable or less than the diameter sound incident 90 degree may show phase cancellation difference may be incorporated at the high frequency for sound arriving of 180 degree. So, if the sound arriving in 180 degree phase shift, then there may be a cancellation of the sound, because it can say that interaction, that you can say the what is said that if it is same phase, it will be amplified, it will be added up, arithmetic sum. If it is opposite phase, it destructive, it will be destructive. So, to avoid that part, we make a small kind of aperture here, and there is a small passage of the air pressure. So, that 180 degree also come in here. Okay. Then, so the directivity pattern of this kind of microphone will be like this, pressure microphone. Then I go to the pressure gradient microphone or velocity microphone. The output of those type of microphone depends on the pressure difference or gradient between the sound waves that hit the front and the back of the diaphragm. So, diaphragm has to be exposed in both sides, so that this microphone will work the pressure difference between this side and this side, pressure difference between this side and this side. Then I call it is a pressure gradient microphone. If I say, if I give you a picture, pressure gradient microphone, diaphragm is exposed on both sides. Example, if you see the commentary microphone, that is a pressure gradient microphone, both side is there. Now, the directivity pattern will come, figure of it with both side of the diaphragm is open. So, I can take the sound from this side and this side, both sides. So, it is a figure of 8. Okay. Now, can I calculate method for determining the pressure gradient? How do you determine the pressure gradient of the pressure gradient microphone? So, it is very simple. This is FR. What is FR? Force on rear diaphragm. So, there is a two diaphragm is exposed both sides, rear side and back side, and this is, so the rear side and, sorry, if you see this slide, there is a mistake in the slides. So, it is the front side, let us say front side, and it is back side. This is front side and this is back side. Let us FF and FR, front side pressure and back side pressure. Okay. Now, so this is the pressure gradient, because the pressure is coming from the same source. Okay. So, this is the pressure gradient Fg. Okay. So, this is Fr, Ff and Fg. Now, if I say this is I draw a 90 degree and this is a x1 and this is x2 and this angle is beta. What is beta? Beta is nothing but a d by lambda into 360 degree. What it is d? D is the length from the front to rear path. So, suppose I make a diaphragm exposed like this way. So, the front is this, back is this. So, front to rear path, that is the d. Okay. So, d by lambda into 360 degree is the angle beta. How the sound is coming? So, if it is beta is that, then and lambda is equal to c by f. So, beta can be df by c into 360 degree. Okay. Now, if I do some arithmetic in here, what is ff? Is nothing but a this distance plus this distance, x1 plus x2. What is x1? X1 is nothing but a fr cos beta, projection of fr on this side. So, fr cos beta, if this is the right angle triangle. So, this is x1 is nothing but a fr cos beta plus what is this length? Hypotenuse minus base root over of hypotenuse. So, root over of fg square minus fr square this sine square beta. Have you understand? This is nothing but a fr sin beta and this is nothing but a fr cos beta. So, this is nothing but a fr sin beta. So, it is ef is nothing but x1 plus 2 x2. So, x1 is fr cos beta and f2 is the base. So, it is hypotenuse root over of this square minus this square. So, Fg, if I simplify this, Fg will come ff square plus fr square, fr square minus 2 ff fr into cos beta. Okay. So, if both are same, if fr is equal to ff, then Fg is nothing but a 2 ff square 1 minus cos beta. Okay, 1 minus cos beta. So, Fg pressure gradient is nothing but a 2 ff square into 1 minus cos beta. So, Fg is very small when f is low and Fg is maximum when its beta is 180 degree. This is okay. So, now I can draw the Fg versus the frequency versus Fg curve, and if you see, this will look like this. Okay. So, in the next class I will discuss about the sensitivity mathematics. So, here I have discussed about the different kind of microphone and their construction, and I discuss about the pressure gradient microphone, pressure microphone, directivity pattern and their directivity pattern of the microphone, sensitivity and their constructional things, and already I have discussed about that transduction, that mathematics, details mathematics. So, when we design the mathematics, the sensitivity will nothing but m0, which will come from that transductional mathematics. Okay. So, next we will see what is the sensitivity, how it measures, then relationship with the sensitivity, GIA, LPA, all kind of things I will discuss. Okay. Thank you.